Starting from this video, we'll talk about gas mover control systems. Gas movers can be compressors or turbines. There are actually two main types of gas movers or compressors: dynamic and positive displacement. Dynamic compressor can be either axial or centrifugal. Positive displacement compressor can either be rotary or reciprocating. Control systems for compressors are very similar to pump control systems. Both need to have capacity control. But despite the fact that we don't need minimum protection for positive displacement pumps, as we have seen in a previous video, we do need it for positive displacement gas movers. Minimum protection for pumps is referred to as minimum flow control. And for gas movers or compressors, it is called surge protection. Now again, for centrifugal gas movers, there are two control systems needed: capacity control and anti-surge control. We'll see this in detail further ahead. There are 5 main types of control for gas movers. These are recirculation pipe, speed control, suction throttling, discharge throttling, and a combination of control methods based on the structure of the gas mover. Take a look at the following table. It shows which methods are technically applicable for which types of gas mover. The first method is recirculation. This is a general control method that can be used for any type of gas mover. In this method, a pipe connects the discharge side of the gas mover to its suction side. A control loop is placed on the pipe. This arrangement looks very similar to the minimum flow protection system we have seen for pumps. But there are, of course, plenty of differences in the details. We'll see this further ahead. The second method is the speed control, or VSD. Again, you can use this method of control for all gas movers. In this method, the shaft speed of the gas mover is adjusted through a mechanism. As it was mentioned in a previous video, the mechanism could be a VFD for electric motors or a governor for turbines. Next is suction throttling. Suction throttling means putting the control valve on the suction side of the gas mover. With a pump, you have the danger of cavitation if you place the control valve on the suction side. But cavitation is not an issue with gas movers. The next method is discharge throttling. This means that the control valve is placed on the discharge side of the gas mover. This method of control is acceptable to use with dynamic gas movers, but not with positive displacement gas movers. Finally, you have special control methods. Unlike the previous 4 control methods, this is not a single control method. Depending on the type of gas mover, a few extra control methods could be available. We call all of these gas mover specific control methods special control. For example, in axial gas movers such as blowers or air coolers, we can adjust the flow rate by changing the pitch or angle of the blades. There will be more about this further ahead. Now, we explained the different types of control that are technically possible. However, not all of them are economically acceptable in each application. Take a look at the second table. It gives you the applicability of each control method. Let's start with recirculation. This method is not very economical because when you recirculate back to the section side, you are expanding the gas and therefore wasting energy. Take a look at this PNID example. It shows a typical recirculation system. Here we have a recirculation line with a check valve, and we have included a cooler on the line because with compression you get an increase in temperature and you may need to cool the recirculated gas before it goes back into the section side of the gas mover. We also have a control valve on this line to prevent all of the flow from going through this attractive route of less resistance. Now there are two options for a control loop here: flow loop as seen here, or pressure loop. And as flow and pressure are interrelated, both of them are theoretically acceptable. The decision of whether to use a flow control loop or a pressure control loop could be based on some other parameters. For example, pressure sensors in general have higher rangeability, and if your flow surges a lot, a pressure loop may be a better option and will be most likely on your PNIDs. The other case is when you are dealing with very high discharge pressures. In such cases, high design pressure flow meters could be overly expensive and not justifiable. This may direct you to use a pressure control loop instead of a flow control loop. Now back to our table. Let's discuss the speed control. This method can be used with all gas movers. The following figure shows the control of a gas mover by VSD, or variable speed drive, when its drive is an electric motor. Some companies use the symbol SC as highlighted here in their PNIDs, meaning speed control. Some other companies use the acronym VFD or VSD. Recall, VFD means variable frequency drive and VSD means variable speed drive. This next PNID example shows the same VSD control on a steam turbine driven gas mover. Here, the device that works to change the speed of turbine shaft is a governor. Now, next, we have suction throttling. Suction throttling can be used for all types of gas movers, but is really only popular with centrifugal gas compressors. Basically, in this control scheme, you will see on your PNIDs a control valve on the suction side of the gas mover. Recall that with pumps, you have the danger of cavitation if you place the control valve on the suction side, but cavitation is not an issue with gas movers. With this method, so suction throttling, there are two options for a control loop: flow loop as seen on the left-hand PNID schematic, or pressure loop as seen on the right-hand PNID schematic. The next method is discharge throttling. Although this method can be used for all dynamic type gas movers, it is not economical. By adjusting the valve on the discharge side of a gas mover, we are partially expanding a gas that we had already compressed and spent money to do so. So clearly, this is a waste of energy. However, this is not much of a factor when dealing with gas movers with small compression ratios, such as fans and blowers. Take a look at the following PNID schematic. Basically, in this control scheme, a control valve is placed on the discharge side of the gas mover. Recall here that this method of control is acceptable to use with dynamic gas movers, but not with positive displacement gas movers. Here again, with this method, you have two options for a control loop: flow loop as seen here, or pressure loop as seen here. For the pressure loop, a pressure transmitter is placed on the discharge side of the compressor. In this case, if the measured pressure at the discharge of the compressor drops below a set point, the pressure controller will trigger a signal to throttle the discharge valve. Finally, the last control method that we're going to discuss in this video is related to special control method. This is a combination of capacity control methods for gas movers that uses some adjustable element in the structure of the gas mover to control its capacity. To be able to explain all of these methods, you need to know the detailed structure of gas movers, which is beyond the scope of this course. However, if you feel like you want to know more, then please check out our bestseller course on centrifugal compressors, Principle, Operation and Design. This course will provide you with a complete understanding of construction details and functioning of centrifugal compressors for a successful operation of your plant and piping system. Before to enroll in, don't forget to ask us for coupon codes. Now, in this course, we will explain only one simple special control method, which is guide vane adjustment. This special control example is applicable only to centrifugal gas movers. Take a look at the following P&ID example. In centrifugal gas movers, there is an element installed in the inlet of the gas mover called a guide vane. By controlling the position of the guide vane, the capacity of the gas mover can be adjusted. To better illustrate this, let's take a look at the following 3D animation. Here you have a cut view of a typical centrifugal compressor. The blue piece that you can see here is the inlet guide vane. And here you can see the inlet guide vane in animation. To have a better picture of this, you can visualize the guide vane as being similar to a built-in control valve on the suction side of the gas mover. As depicted here, by controlling the position of the guide vane, the capacity of the gas mover can be adjusted. When we talk about surge control, we have the same problem as with centrifugal pumps, meaning providing protection against a minimum condition. For centrifugal pumps, this means providing minimum flow control. But for an axial or centrifugal gas mover, we have to deal with a surge problem by providing anti-surge protection control. Take a look at the following P&ID schematic. It shows a simple anti-surge system. Please note that the anti-surge control could be more complicated than what is shown here. This is because surge is one of the fastest phenomena in process plants. In this example, you have a recirculation line, a control valve on this line to prevent all of the flow from going through this attractive route of less resistance, two pressure transmitters, one placed on the suction side and one on the discharge side, to monitor the pressure differential across the gas mover. Then you have a flow transmitter at the section of the gas mover. If the pressure differential drops below a certain set point, or if the flow rate at the inlet of the gas mover drops below a certain set point, Then the flow controller that you can see here will trigger a control signal to open the control valve on the recirculation pipe and allow some of the gas to flow back from the discharge into the section of the gas mover. By doing so, this control system provides protection against a minimum condition. In other words, provides protection against surge. Now, we don't need an anti-surge system for low-pressure dynamic gas movers like fans or blowers. We don't need them for positive displacement gas movers either. The rule of thumb to use is that an anti-surge protection should be applied if the pressure differential around the dynamic gas mover is more than 15 kilopascal or 0.15 bar or 2.17 psi, and that the gas mover's required power is more than 150 brake horsepower.